Okay, 2006B, question 5. This is the same equilibrium lab that we did. A student carries out an experiment to determine the equilibrium constant by colorimetric or spectrophotometric analysis. The production of the red species FeSCN plus 2 is monitored. Okay, what's the optimum wavelength? Remember now, we've been giving you these in this lab, but SPEC 20 labs or spectrophotometer labs are supposed to be done at maximum absorbance because that stretches out the scale. And so this lab, question A, what is the optimum wavelength for this experiment? Optimum means best. You could do it, here or here. It's just that if you did it like at 600 nanometers, your graph would have a max value of like let's say 0.01, and then when you cut that in half and cut it in half, you wouldn't be able to see it. And so the answer to this question is 450 nanometers is the answer. What is the optimum wavelength? Justify your answer. Spectral let me do photometric, spectrophotometric labs work best at maximum absorbance. And remember, here is Beer's law. The absorbance is a product of A, which is a function of the molecule, and then B is the path length, and then C is the concentration. And this is called Molel, what is it? Molel constant. And so the bigger A is, the more, you want to have a graph that is linear like this, not a graph that's linear like this. And this is why we do it at maximum absorbance. No other reason. A calibration plot is prepared at the optimum wavelength, the data below. So here we go. When the concentration is this, it's this. And they actually did this so because on the old test you didn't get a calculator. And so they want us to do this plot. And so if you look, when I was taking this practice test the first time I did it, there's 1, 2, 3, 4, 5, 6 lines. And if you go back, you have to go from 0 to 18. So it makes sense to me that this would be 3.0 times 10 to the negative fourth. And then this would be 6. I don't have room to write it. So this would be 9 times 10 to the negative fourth. This would be 12, and this would be 15 times 10 to the negative fourth, and then this would be 18. And so now when we go back and plot this 1.1 versus 0.03, so it looks to me like our first point is, so if this is 3 and this is 0, this is about 1.1, about a third, and then 0.03, this is 0.05. So I'm thinking our first point is going to be about here, 1/3 of the way. Hold on, maybe that's a little, 1/3 of the way, and then up to 0.03. So that's the first one. And then the second one is 3 is 0.065. So right on the 3 line, and here's 6.065, probably right about here. Going back, 8 is 0.16, so here's 9, so here's 8, and then 8 is here's 0.15, here's 0.16. Going back, 12 is 0.239, so 12, which would be right here, 0.2, 0.25, so 0.239 is about here. And then 18 is 0.34, so 18, which is out here, 0.34 is about here. And so then this will be hard for me to do, but without a ruler. But let's say that this is our line of best fit. This is important. Um, really, I don't like this. This is bad for them. They should have concentration in moles per liter, something like that. You're always said units in parentheses. Okay, now using the line that you drew. And so they want to know what the concentration would be if the absorbance was 0.3. So I'm going to come over here. I'm going to grab my line, and it looks like the answer is 1.5, or sorry, 15 times 10 to the negative 4 moles per liter, which drives me insane because this would be 1.5 times 10 to the negative 3. They just wrote it in not good form so that you guys could graph it. And that's that question. What's the equilibrium constant? Well, the equilibrium constant, remember, it's right over left. All right. This is the first time I took this test, I did this problem wrong. So here's the deal. Here's the equation. Let me write the equation and tell you um, what an idiot I was. So I'm going to really space this out. This is very much like your lab. Um, and so I think I was treating this like a titration problem. So here is my ice chart. Sorry, this isn't spaced very well. But it says, okay, Fe plus 3 and SEN are both, in the beginning, these are both 1.6 times 10 to the negative 3, 6.0 times 10 to the negative 3. And in the beginning, this is 0. And if you remember, we did this lab. You did it with Higgins. This stuff is colorless. This stuff is colorless. This is a brownish red color. Now, remember, photometric analysis only works if the solution is colored, because we know, if you've ever played with food coloring, the more food coloring you put in water, the darker the color gets, that it's a function of concentration. All right, then it says the absorbance of this solution is measured and the equilibrium concentration of this is, here's the thing, these are initial, this is equilibrium. They're telling you you got to go to the E row and the SCN column. And so then this is 1.0 times 10 to the negative 6. Remember, this is question 5. This was a question that kids had to do in the past without a calculator. Well, this, and then this has to be negative 1.0 times 10. Is that negative 3 or negative 6? Oh, no, sorry. These are negative 3. And this is negative 3. This is bad. Mrs. I need to get an eraser because this would make the math difficult. So interestingly enough, back when they took this, kids had to do this without a calculator, and you'll see why it's not so big. So notice 0 plus 1.0 times, so then these all have to be the same because it's a 1 to 1 to 1 mole ratio. Now remember, if there was a 2 here, you double this. All right, now 6 times 10 to the negative 3 minus 1 times 10 to the negative 3, this would end up being 5 times 10 to the negative 3. And this would end up being 5 times 10 to the negative 3. And now we're going to go up to this answer below, and then we're going to plug in this for here, and this for here. And so what happens is I'm going to hit extend page. KC ends up being 1 times 10 to the negative 3 over 5 times 10 to the negative 3 times 5 times 10 to the negative 3. Now they had to do this without a calculator. I would just do it with a calculator. This comes out to be 40. Here's how you would do it without a calculator. 1 times 10 to the negative 3. And then this would be 5 times 5 is 25. And 10 to the negative 3 divided by 10 to the negative 3 is 10 to the negative 6. And then just if, so I'm going to make this 10 to the negative 6, so this cancels. but if you make this 1,000 times smaller, you have to make this 1,000 times bigger. And so then how many times does 25 go into 100? 40. So 25 goes into 100 4 times. And so that's how you would do it without a calculator. That won't ever happen to you guys, so good for you. If the student's equilibrium of FCN plus, so of unknown concentration, fades to a lighter color before the student measures its absorbance, will the Kc value be too high, too low, or unaffected? Justify your answer. Now I'm going to go back down here and show you your flow. So if you wait too long, the absorbance is too low. Okay. Now, because Beer's law says that absorbance equals ABC, if you solve this for C, C is absorbance over A times B. These are constants. Well, if A is too low, then C is too low. And if C is too low, remember Kc equals the concentration of the red stuff, which is this stuff. Sorry, SCN plus 2. This is what we're measuring. Remember the two, if you remember doing this lab, the two reactants are colorless, but then when you put them together, you make a colored solution, and over time this will fade. So Kc this is the formula for Kc. If you go up there and look, all right, so then if the concentration of this is too low, and that's in the numerator, then Kc is too low. Now that's my thought process. Now here is my answer to the question. First question, you answer the question. The calculated value of Kc would be too low. Now here's how you justify it. The absorbance would be too low. Therefore, the concentration of the FeSCN plus 2 would be too low, and Kc would also be too low. Now this is kind of your scratch work, but it wouldn't be bad for the graders to see that. But this is your answer. And I think that's it.